Bismillah ar-Rahman ar-Rahim. N is a positive integer. The floor of the square root of 9n plus 8 is equal to the floor of this sum, the square root of n plus the square root of n plus 1 plus the square root of n plus 2. To prove this identity, consider the square root function. The first derivative is 1/2 alpha to the minus half. The second derivative is minus 1/4 alpha to the minus 3 over 2. This is strictly negative for every alpha greater than 0. The square root function is strictly concave. If g is strictly concave, then g of lambda 1 alpha 1 plus lambda 2 alpha 2 plus lambda 3 alpha 3 is greater than or equal to summation I from 1 to 3 lambda I g of alpha I. The lambdas are non-negative and their sum is equal to 1. This means that what we have here is a convex combination. We have equality if and only if alpha 1 is equal to alpha 2 is equal to alpha 3. Let's apply this inequality. The alphas in our case are n plus 1, n plus 2. They are distinct, hence we have a strict inequality. In our case, we set lambda 1 equal to lambda 2 equal to lambda 3 equal to 1/3. The concavity of the square root function implies that 1/3 square root n plus 1/3 square root n plus 1 plus 1/3 square root n plus 2 is strictly less than the square root of the convex combination. So we have 1/3 times n plus 1/3 times n plus 1 plus 1/3 times n plus 2. This bracket here is 3n plus 3. The right hand side is the square root of n plus 1. Multiplying both sides of the inequality by 3, we get that the square root of n plus the square root of n plus 1 plus the square root of n plus 2 is strictly less than 3 times the square root of n plus 1, or the square root of 9n plus 9. We have now an upper bound on the sum of the square roots. Our next step is to obtain a lower bound. Take the sum of the square roots and then put here 3 square root n plus 1. Note that this is exactly the upper bound that we have. We still have these two square roots and we need to subtract twice this square root. We write the remaining terms in this particular way. Square root of n plus 2 minus square root of n plus 1 minus, between brackets, the square root of n plus 1 minus the square root of n. Note that the square root of n plus 2 minus the square root of n plus 1 times the square root of n plus 2 plus the square root of n plus 1 is equal to the square of this quantity n plus 2 minus the square of that quantity n plus 1. This bracket here can be written as this difference, which is equal to 1 divided by the sum of the square roots. We apply the same to this bracket here. It is written as n plus 1 minus n divided by the sum of the square roots. Both numerators are equal to 1. Till now we have an equality. We want a lower bound. This is reduced in value if we replace n plus 1 in the denominator by n plus 2. If we increase the value of the denominator, then we reduce the value of the fraction. This is lower bounded by 1 over the square root of n plus 2 plus the square root of n plus 2. That's 1 over 2 times the square root of n plus 2. We also need to lower bound this term here, but there is a minus sign. To get a lower bound, we need now to reduce the denominator. We replace this square root of n plus 1 by the square root of n. A lower bound on the sum of these 3 square roots is 3 square root n plus 1. Then we have 1/2, 1 over square root n plus 2 minus 1 over square root n. We will apply the same idea again. 1 over square root n plus 2 minus 1 over square root n times 1 over square root n plus 2 plus 1 over square root n is equal to 1 over n plus 2 minus 1 over n. This bracket here is equal to 1 over n plus 2 minus 1 over n. Downstairs, we have the sum. We can further lower bound by decreasing the denominator as the numerator is negative. This is achieved by increasing this n to n plus 2. This term here is 1/2. Multiply the numerator and denominator by n times n plus 2. In the numerator, we get n minus n plus 2. In the denominator, we have 2, then n plus 2 divided by the square root of n plus 2. That's the square root of n plus 2. We have minus 2 upstairs, and so this is equal to minus 1 divided by 2n times the square root of n plus 2. This term here. The lower bound on the sum of the 3 square roots is 3 times the square root of n plus 1, or square root of 9n plus 9, plus this quantity here. Question: can we make this quantity strictly greater than the square root of 9n plus 8, at least when n is large enough? The answer is yes. We have this inequality if n is 3 or more. To prove this, consider the cubic polynomial x cubed plus 2x squared minus 9x minus 9. The coefficient here is positive, then negative, then negative. We have one change in sign. By Descartes' sign rule, this polynomial here has one real positive root. Evaluating this polynomial at 2 and at 3, we get a strictly negative number at 2 and a strictly positive number at 3. This polynomial at 2 is minus 11, at 3 is 9. It is 0 somewhere between 2 and 3, but then it increases to infinity as x tends to infinity. Thus, this polynomial is strictly positive when x is 3 or more. Changing x to n, we have n cubed plus 2n squared minus 9n minus 9 is strictly positive when n is greater than or equal to 3. N squared times n plus 2 is strictly greater than 9n plus 9. Taking the reciprocal square root of both sides, 1 over the square root of 9n plus 9 is strictly superior to 1 over n times the square root of n plus 2. Multiply both sides by 1/2. This quantity here is 1 over square root 9n plus 9 plus square root 9n plus 9. We can have an upper bound by replacing this 9n plus 9 by 9n plus 8. Multiply numerator and denominator by the difference of the square roots. This is 1. What we get from here is that the square root of 9n plus 9 minus the square root of 9n plus 8 is strictly greater than this term here, 1 over 2n square root n plus 2. Moving this to the right-hand side and that to the left-hand side, we have that the square root of 9n plus 9 minus 1 over 2n square root n plus 2, this lower bound that we have earlier, is indeed greater than the square root of 9n plus 8. The proof is for n greater than or equal to 3. However, we can check the remaining cases when n is equal to 1 and n is equal to 2. We discover that actually this inequality is true for any positive integer n. The sum of the square roots is living between the square root of 9n plus 8 and the square root of 9n plus 9. The floor function is a non-decreasing function. If x is less than or equal to y, then the floor of x is less than or equal to the floor of y. We have these two inequalities from our previous work. If we take the floor of all sides, we get that the floor of the sum of the three square roots is greater than or equal to the floor of the square root of 9n plus 8 and is less than or equal to the floor of the square root of 9n plus 9. Our goal is to show that there is equality here. What is the distance between the square root of 9n plus 9 and square root of 9n plus 8? If we take this difference, apply the same idea we have seen earlier, that a minus b is equal to a squared minus b squared over a plus b. We find that the difference is equal to 1 over the sum of the square roots. We can get an upper bound by replacing 9n plus 9 by 9n and 9n plus 8 by 9n. This is 1 over 6 square root n. And because n is greater than or equal to 1, 1 over square root n is less than or equal to 1. This means that the difference between these two square roots is upper bounded by 1 over 6. It may happen that 9n plus 9 is a square number. For instance, if n is equal to 3, 9n plus 9 is equal to 36. The square root is equal to integer 6. If the square root of 9n plus 9 is an integer, then the square root of 9n plus 9 minus 1 is the preceding integer. What about the square root of 9n plus 8? According to this inequality, the square root of 9n plus 8 is within 1 over 6 from this point here. So this separation is at most 1 over 6. Where is the sum of the three square roots? It is somewhere here between these two numbers. Our conclusion is that the floor of the sum of the three square roots is equal to the floor of the square root of 9n plus 8. These two floors are equal to this integer here, the square root of 9n plus 9 minus 1. What if this square root is not an integer? The claim is that this floor of interest is still equal to the floor of the square root of 9n plus 8. What is a challenge to this claim? Here is the square root of 9n plus 9. Now it is not an integer. Here is its floor. If the square root of 9n plus 8 is here, we have no problem because the sum of the three square roots is between these two guys. Now with the same floor. The challenge is when we have the square root of 9n plus 8 here below the floor of the square root of 9n plus 9. And the sum of the square roots, let's say, is here. In this case, this floor is not equal to the floor of the square root of 9n plus 8. However, this picture here is impossible. Suppose that we have something like this. The floor of square root 9n plus 9 is strictly greater than the square root of 9n plus 8. And because this square root is not an integer, then we also have a strict inequality here. Can this ever happen? Square all sides. We get that 9n plus 8 is less than the floor of the square root of 9n plus 9 squared, which in turn is strictly less than 9n plus 9. The floor function produces an integer. When we square an integer, we have an integer. This statement here tells us that there is an integer living between the two integers 9n plus 8 and 9n plus 9. But these are two consecutive integers. There can never be an integer in between. This cannot be true. In all cases, the floor of the square root of n plus the square root of n plus 1 plus the square root of n plus 2 is equal to the floor of the square root of 9n plus 8. As an exercise, show that this floor is also equal to the floor of the square root of 9n+7. The key idea to show this is to note that 9n+8 is never a square number. 9n+8 is congruent to 8 or -1 modulo 9, and -1 is a non-quadratic residue mod 9.